Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. We are here trying to get you to do some cycloalkanes. Think about bicycles, wheels, rings. That's what we're going to do here, cycloalkane conformation. So kind of rings made out of alkanes. So, well, what's the smallest ring you can make? How many carbons should you have? Well, one carbon obviously is just like a dot. 2 carbons is going to be a line. You need at least 3 to make a cyclo compound, right? So let's start with the 3 carbon cycloalkane. So that would be cyclopropane, 3 carbons. So the first one is going to be cyclopropane. 3 carbons like this, and each one of them would be connected to each other like that. And then you need to have 4 things. And you would have hydrogens or any other atoms, but let's put hydrogens for convenience. That's cyclopropane. Now, it does look kind of squished in here. Is it squished? It is squished in there. So when you have 3 in a ring, it wants to be 109.5, but you know that in an equilateral triangle, the angles are going to be 60. So how do you squeeze 109 into a 60? It's really strained. First of all, you can see in 109, they're further apart. But when you squish them, these bonds are basically electrons that are repelling each other. So there's a lot of angle strain. That's what it's called, angle strain. So deviation from 109.5 to either smaller or even a bigger. When you do a bigger angle, then you're going to squish the other bonds. So when you have a deviation from the hybridization angle, it causes orbitals to be constrained in a way that it's away from their natural state, and it causes a higher energy repulsion. So it's unstable, and they want to come apart like that. So when you have cycloalkanes, the main thing that increases the energy here would be the angle strain that we just talked about. And also, if you look at this, you can see this hydrogen and this hydrogen are eclipsed. This hydrogen and this hydrogen are eclipsed. So all around the ring you have eclipse, and there's no way that you can kind of bend out of the way to get out of that eclipse. So you have lots of eclipsing, 3 and 3 here, and then the angle strain. The eclipsed would be here, these 2 being parallel to each other. These 2 bonds over here are going to be causing some torsion. So let's look at angle strain, which is a new thing. Angle strain. We talked about torsion and the other things when we talked about open chain, butanes, and so on. But angle strain is when you are confined to rings. So angle strain is when deviation from, so this is important, so I'll write it down, deviation from ideal hybridization angle causes repulsion between bonds within a ring, within a cyclo or ring compound. This higher energy is called angle strain. It's also called Bayer strain. I think it was like von Bayer, sounds very German, but he's the guy who discovered it. So angle strain, so this is also called Bayer strain, is equal to the increase in energy due to angle strain. Increase in potential energy due to angle strain that is deviating from the hybridization angle. I'm going to draw this molecule in like a side view, which means you will have hydrogens here up and hydrogens down, and they are all going to be eclipsing each other. And the angle here is going to be 60 degrees. Actually, theoretical angle is 60 degrees, but it kind of overcomes that a little bit by kind of bending these. I can't bend these, I'll just break them. They bend as like a banana bond. Here you go. I need 3 bananas here, but they kind of bow out in a sense. So the angle is more like closer to 100 degrees. But banana bonds make it about 100 degrees. So if you do what you call a Newman here, if you do a Newman for this, the Newman is going to have a dot and a circle. So if you look through here, a dot and a circle, and over here you're going to have a very big eclipse. So between this and the back carbon, you'll have kind of a big eclipse. Now the banana bonds may relieve it a teeny bit, but not much. So how do we know how unstable or stable this is? What we can do is we can actually burn it and see, when you burn it, what would be the combustion energy. So here is the shape, and here's theoretical shape. Here's the actual shape. I'm going to put it over here, and here is a Newman. When you burn it, what do we mean when like burning it? You can take this, let's say this is going to be C3H6, and then you put some oxygen, and just like you have in your propane tank, you kind of burn up your carbon into carbon dioxide, and you are going to burn up hydrogen into water. That's what you do when you heat up your home or use anything that's a fuel. So here you should get 3 carbon dioxides and 6 hydrogens, so therefore you should have 3 times 2, 6 water molecules. But that really won't balance out the oxygen here. So 3 times 2, 6 oxygen atoms, and 3, 9 oxygen atoms. So that's going to be 9 oxygen atoms, but this is molecules which have 2 atoms per molecule, so that's 9 over 2. So you multiply the whole thing by 2, and that's going to give you 2 C3H6. This is just to balance it out, plus 9 O2. That's going to give you 6 carbon dioxide and 6 water molecules. So now we got 6 and 12, 18, which is what we have here. For 1 mole of this, we are going to get a combustion of 2091. So plus delta HC, this is going to be for 2 moles, but if it's for 1 mole, we'll just delta H combustion, kilojoules per mole, is going to be minus 2091. Well, that's pretty high. Well, that's why we use it as a fuel. We want a ton of energy coming out, even for the teeniest molecule here. And nature's provided that. So if you want to compare all of these, it would be much better off trying to find out what's the combustion energy released when a CH2 is burnt, a single CH2. So this is delta H C per CH2. That means here you have 3 of them. So if you divide that by 3, you're going to get minus 697. Then we will compare the others with this and see whether it's more or less. All right. So let's put our banana bonds away and turn to cyclobutane. So this is cyclobutane. Cyclobutane is going to be, as the name says, a ring, cyclo, with 4 carbons, butane. And so if you have 4 carbons, it's going to be a square, a box, a square really. And so you're going to take a theoretical angle here for this. It's pretty obvious. It's a right angle, so it's 90 degrees theoretical angle. But this is going to look like this. It's hard for me to actually do that. There you go. So, well, you can see First of all, this is going to be a little strained. It's hard for me to even make it flat because it's a little strained there. And over here, these are all eclipsed. And you can see at the bottom also, these are eclipsed if I draw it out like this. So what is it going to do to relieve itself? Well, unlike the 3-membered ring, the 4-membered ring can actually pucker like this. So when it puckers, you can see that the torsion is relieved a little bit. This is more like maybe a 20-degree. And it can go this way as well. This is called puckering. So the actual butane's never really going to be like this for too long. This is just an intermediate state. It's going to be either here where it's puckered, and you can see the eclipsing here is relieved to some extent, even though it's not fully staggered, it's somewhat staggered. And then when it goes in the other direction also, it's going to be staggered. All right, so over here, we can draw this out like this. So here's your hydrogen, 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 and hydrogens here. Now, if you look at it through here, and let's say I'm going to compare this hydrogen and this hydrogen here, and I'm going to look through here, what am I going to see? On the Newman, you're going to see a puckered arrangement. So this is going to be what you call a puckered cyclobutane conformation. And the angle is going to be probably close to this, maybe a little bit more. I don't really know what the angle is, but it's, I would say, greater than 100. So, and we can draw a Newman projection through here, through one of them. We can do this and look at it through 2 carbons, dot and a circle. So if you draw the dot and the circle, it's going to look like this. So let's draw the puckered guy here. So over here, you'll have hydrogen going on top, and this is going to come down, and you're going to have a back carbon as a ring, and you can put your hydrogen here, and you can see that it's going to be kind of a little bit staggered, not a whole lot staggered. There you go. So that's your Newman projection. What about the energy? What do you think? Is it going to be better or worse than this? Well, you can see that the angle is going to be relieved to some extent, and therefore it's going to be, a little bit better than this. You're getting bigger, the angles. You're getting closer to your theoretical 109.5. So here the energy for this is going to be 2721 minus 681. So the energy actually got lowered. Is that a good thing? Yeah, it's almost like this guy is on a hill that's higher because it's already got a lot of energy, so it falls to carbon dioxide and water, which all of them, when they burn, go to carbon dioxide and water. The bottom line or the valley is the same. So this guy is a little higher on the hill, so the fall is greater. It was very unstable, so it releases a lot more energy than a molecule who is lower on a hill, and so it has less energy to release when it burns up. So the lower the heat of combustion for a hydrocarbon, the more stable it is before combustion. After combustion, they all go to the same baseline, carbon dioxide and water. All right, so let's move on to the next one, which means I got to add one more carbon here. let's go to the next, what you call a homolog, which is going to be having 5 carbons. And so if you have 5 carbons, then the angle is going to be 180 minus 360 over 5. That's going to be 108, which is kind of perfect because 109.5 is what you want. So the angle strain here would be almost 0 because it's almost the ideal hybridization angle. There's really no deviation there. However, look at it on the side. What do you see? A lot of eclipsing, right? So it's really not very happy with all of these eclipsing bonds. So because of the eclipsing energy and the torsional strain here, it's going to relieve itself by going up like this, like a envelope that's, you know, when you open it and you leave it on the table, it looks like that. That's called an envelope conformation. And it's not just stuck in here. So this one would go up, then it would come down, the next one would go up, then that would come down, and the next one would come up, and that would go down, and then they go around the ring like this, like a, you know, taking turns, ring around the rosy kind of thing. Go around the ring like this on an envelope conformation. That relieves some of the torsion, and you can see even here, looking through a Newman, it's not completely eclipsed, it's staggered, and this goes really fast around the ring. The angle strain is going to be fine. Let's see cyclopentane, and that is going to be 5 carbons like that, and it's going to have a theoretical angle of 108, and so that's pretty much ideal. But it's going to not be happy because of all of the eclipsing, so it's going to go and just like bend out of the way. And so here it is. You can see that these are going to take turns going up and down, and you would have some degree of relief from that terrible torsion. So if I'm, let's say, looking through here, there's a dot, and there's a hydrogen up and a hydrogen down, and then you don't see this because that's hidden behind that dot, and then you'll have a hydrogen up and a hydrogen down like that. And so that relieves some of the strain. And so here is your other carbon, and here is your other carbon over here. All right, so there's your cyclopentane, and this is called the envelope conformation. Staggered CH bonds relieve torsion. You can see 5-membered rings have been around for 3.5 billion years in bacteria, ribonucleic acid, right? They have RNA. So one of the most stable forms of a cyclo is 5. But it's not the most stable, and we will see why in a minute. 6-membered rings. What do they want to look like? Do they want to be flat like this? Of course not. Well, now this is going to be 120 degrees, so not that great, because 120 is a little bit too much of a deviation from 109.5, or about 10 degrees off. So therefore, it's going to pucker just like that, but if they puckered on the same side, you're going to be bumping, and this is a boat. You can take a boat ride along the Thames, or you can pucker in opposite sides, and that's what they like to do. They like to be puckered like this, and that's called a chair for good reasons. You can see how you can lie down on here all day and watch TV, right? It's a chair. So the chair form, when you look through, you can see it's completely staggered. Each one of them is a completely staggered carbon-carbon bond, like in a butane. So that's the best form, because when you have a staggered conformation, you don't have any torsion, fully staggered. And the angle also is 109.5. You can't get better than this. All right. So let's draw it out. Cyclohexane. Best. Okay, hands down, that's the best. And then the theoretical angle is going to be 120. And so it goes into relief, that it goes into a chair. Relief, relief, torsion, it goes into a chair. All right, does it get stuck on this chair? Not really. It gets up and then goes to the other chair. And kind of, and then goes to this chair and goes back and forth, back and forth. So there's a lot of conformations possible, and the best are the two chairs. So the chairs are going to look kind of like this. So here you're going to have this going up and this coming down, and then it goes to the other chair, flipping like this. So there again you're going to have the chairs then going in the other direction, and we will learn how to draw the chairs. And these hydrogens are going up, vertically up like these red ones, and then you'll see these are on the side, going down, pointing down. And over here you will have some as well, pointing up, and then you will have these pointing down. And there is a nice 60-degree angle when you draw the Newman projection between this and this, which is the ideal one. So this, looking at it through here, that's your dot, that's your circle, and you'll have a beautiful, very nice 60-degree angle between this and this dihedral angle, which makes it near perfect. You can't get better than this. So this is what we did for a butane. So that's a butane, and we can draw one on the other side as well, and we will do that later. I'm just going to do this for right now. This is going to come over here, and you are going to do that. So staggered, completely staggered. And then the angles, bond angles, about 109.5. This is going to be the most stable. Let's look at the numbers, see if they show that that is the most stable. So for cyclopentane, this was 3291. Well, this is a bigger number because this is for all 5 carbons, but per CH2, if you divide this by 5, that's going to be minus 659 kilojoules per mole. And then over here, this is going to be minus 390.20, and per CH2, it's going to be minus 653. So you can see it's going down, but the biggest gap is here. When you have a little bit more flexibility in that ring, it relieves a lot of the torsion. And the bond angle strain is almost 0. Over here, there's no angle strain and no torsion. That's the best one to be. That's why we all sit on a chair. It's the most relaxing position. No angle strain and no torsion. It always says relieves torsion. What about 7? If it's coming down, shouldn't it keep going down when you add more and more? Let's look at A7. Let's take a 7-membered ring. It's kind of a handful here, and it can go in so many different ways. So if you have it all flat, that's not really good, because now the angle is actually way bigger than what you would want it to be. So now the angle in a cycloheptane is going to be theoretical angle is going to be 128 degrees. So it's going to be way more than the ring can handle. So it's never going to be flat like this. it's just going to be puckering here and going into a lot of different conformations. So we can draw these out as kind of a chair with a 4-membered lip like that. So over here you can see that's kind of, and it goes around the ring like that, and so it relieves torsion and it's a little bit more stable. And the energy for this is going to be, well, is it going to be more or less? What would you predict? Because we don't have this perfectly staggered conformation here, now the inner angle is actually too big, so it's going to be pushing out. Now you don't have perfectly staggered CH bonds around the ring. So there's a little bit more torsion now and a little bit more angle strain. So torsion and angle strain higher than in cyclohexane, in a chair cyclohexane, because it kind of disrupts that chair by having that extra carbon. So because of that, the energy actually now starts to go up, minus 657 per CH2 and 4599 for the whole molecule. Divided by 7, you're going to get this. So therefore, it's going to be a little bit unstable, and you will see when you go to 8, the energy starts actually going up, and then eventually you will, when you come to 12, you'll have like a decalin kind of structure, and then it comes back to where the chair is. So let's kind of graph the energies here to see the trend. So minus 697. And so this is going to go down here, 1, 2, 3, and then rock bottom, and then it starts picking up. So here's our energy trend here. All the way down, and then it starts picking up. So that's one of the reasons why most of the molecules in nature are here, natural molecules, 6-membered rings, which is 2/3 of our food, and wood for our housing and clothing, cotton, all of these things mainly here. 5-membered rings are also very stable. We have them in our DNA, RNA, and lots of 5-membered ribose sugars. Even the sucrose that your table sugar has got a 6 and a 5-membered ring. So you can see nature has chosen these because they're the most stable and they are the most, versatile, flexible molecules out there in nature. So guys, if you're wondering how I came up with these angles, this is probably something you did in 5th grade. So the internal angle of that shape is going to be 180 minus 360 over n. N is the number of sides. So when you have a torsion in a ring, when you have torsion between 2 eclipse bonds, it's also called a pizza strain. So we learned 2 different new terms today. Bayer strain, which is the angle strain, and pizza strain, which is the torsion strain in rings. So in summary, I just wanted to tell you that when you have ring structures, certain conformations are preferred over the others, and the reason for that would be the amount of angle strain and torsion it experiences in its most stable ring form. Cyclohexane has almost 0 angle strain and almost zero torsional strain, so that's the most preferred. And cyclopentanes have almost 0 angle strain and a teeny bit of torsion, but it relieves that through these envelope conformation. Same here, puckered. The cyclopropane, of course, is fixed. There's no way it can wiggle around. So that's one of the most unstable bonds out there, is the cyclopropane CC bonds, and they can actually pop up and react. I mean, that's unusual for an alkane, right? And then as we go along, you can see that the perfect staggering that you see in a 6-membered ring is lost here. And so it gets a little uncomfortable and it keeps going up. All right, so we will see you soon.